So, welcome to Lecture 7 in our series on special relativity, electrodynamics, and general relativity. In Lecture 7, we'll be boosting the electrostatic force to generate electromagnetic fields. We'll understand the origin of magnetism, and then we'll study some more formalism. We'll study more about four vectors, so we can phrase the things that we learn in a general fashion in a way which is manifestly covariant. Okay, so the first exercise we're going to do is to take a charge and boost it to a velocity v, and then observe it in the lab frame. Okay, we want to see what the electric field looks like from that perspective. We'll do this exercise, then we'll use it in the second part of this lecture, where we will be considering a source for the electric field and a sink for the electric field. Okay, and both will be moving in the lab frame, and we'll discover that special relativity predicts magnetism. Okay, and we'll see the formula for the magnetic field, understand it in terms of the electric field, and see that it's generated by the velocity of the moving source. So that's the goals of the exercises that we'll do. Now later, we're going to get much more ambitious. These are just traditional types of applications of boost to understand particular phenomena. After we understand some particular phenomena, we're going to get much more ambitious, okay, and try to break the shackles of typical discussions in textbooks and go to the source. And we'll find that the source will be local differential equations, and when we boost those from one frame to the other, we will get the fundamentals of electrodynamics, not particular cases, but the general equations and rules of electrodynamics will handle all situations and all cases. It's known as Maxwell's equations, and then we'll be pursuing that later. But for the time being, we're taking little steps in that direction. So let's take our first step. So we imagine a charge at rest at the origin in the frame S prime. Remember, the frame S prime is always moving to our right at a velocity v. The charge is at rest, and so we know what the force will be in that frame. The charge has been there a long time. We have a stationary situation, and the force is given by Coulomb's law. Okay, so the force is proportional, constant, times the product of the charges divided by a distance between the charges, and multiplied by a unit vector between the charges. Okay, so the force between two charges is attractive or repulsive along the line of sight between the two. Okay, so I consider the source of the electric field to be at rest in the frame S prime, but I'll take a Q2, which will actually be moving in an arbitrary fashion, okay, from the perspective of S prime. It'll be subject to an electric field that's written here, generated by the charge Q2. But I'll be interested in it at that instantaneous moment, okay, where Q2 is at a position R in the frame S, and it's instantaneously at rest. Okay, so Q2 is being pushed around by the electric field generated by Q1. Okay, but I choose my frame S so that at the time t equals 0, t prime equals 0, when the origins of the two frames S and S prime coincide, that it's at rest. That defines my frame S. Okay, and that's the interesting situation for me. I want to see what the electric field does in the lab frame. Okay, and so I want the particle not to be moving in the lab frame. In the next part of the lecture, we'll imagine that the particle is moving in the lab frame, and that will introduce magnetic forces. But for the moment, if the particle is not moving in the frame S, it's just sitting there, okay, then in that frame, there's only electric effects, as we'll be discussing. Okay, so here's the situation. In the frame S prime, my particle Q1 is sitting at the origin. Okay, it's been there a long time. I have X prime axis, Y prime axis, and Z prime axis. My boost is along the X prime or X direction. My distance R prime will point to the position of Q2 at the time, T equals T prime equals 0. And I'd like to know what the electric field is for various options of R prime, okay, at the time where Q2 is at rest in the frame S, okay, but it's at various, I can imagine it being at various different positions. It's an easy problem. It's easy. Why? Well, because the charge Q1 is at rest in S prime, so I know what the electric field or what the force is in the frame S prime. It's just given by Coulomb's law, right? You have a charge at rest. It's been there a long time, and then you know what the force is, and I've written that down and discussed it already. So I take that force in S prime and write it down in Cartesian coordinates, and here it is, okay? And in this, when I take the X, Y, and Z components of the force, I have to write the unit vector in the X, Y, and Z direction, okay? And that's what's done here. X hat, unit direction in the prime frame is just the 3 vector of X prime, Y prime, Z prime over R prime. That makes it a unit vector, and it points in the appropriate direction. Okay, so that's pretty easy. So now if I have a force in the frame S prime, I know how to get the force in the frame S. Right? We know how to transform forces from one frame to the other. And this is a particularly simple example because the charge Q2 is not moving in the frame S at the time t equals 0. Okay, so I transform to S using the fact that Q2 is at rest in the frame S at that time. So just look back at your general formulas for how to transform forces from one frame to the other. Okay, it's nothing special to electrodynamics. This would happen in any kind of theory. We're just transforming forces according to the rules of special relativity. We don't know the origin of the forces, but the forces, their transformation property is dictated by the properties of special relativity. Nothing special for electrodynamics. I could do this for gravity as well. Once I discovered dark matter, I could do it for dark matter. Whatever. Okay. And so when I do that, okay, I'll find that F sub x is F sub x prime. The force in the x direction is unaffected by the boost, and the forces in the transverse direction are affected by a factor of gamma. Remember, gamma for the transformation is 1 over the square root of 1 minus v squared over c squared, where v is the relative velocity of the two frames. Okay, and so there you have it. And in the textbook, you'll have problems where you'll come to these transformation laws in simple arguments, not relying on the general arguments and taking special cases, as I'm imagining here. There's always lots of ways to do these problems, and the problem sets and the problem solutions illustrate that. But in the lecture, we have to just rely on the general formula and keep moving. Okay, so let's see. So what do we need here? Well, so I have these expressions for f prime, and they're written in terms of x prime, y prime, z prime, and r prime. So I better find those out in terms of the coordinates in the frame S, so that I can write down the force in the frame S in terms that make sense in that frame. Well, that's pretty easy to do. Okay. For example, at t prime equals t equals 0, the origins of these two frames coincide. That's how we set things up. And so I'll take the general Lorentz transformations for x, y, and z and t. uh, for that situation, and then I'll set t equals t prime equals 0. The origins coincide at that moment, and the Lorentz transformations simplify appropriately. I find that x prime is equal to gamma times x. Okay, well that's just Lorentz contraction. X is equal to gamma prime. X is equal to x prime over gamma, right? X prime is the distance in the moving frame. That's a proper distance, okay? And then when observed in the frame in which that distance is moving at a velocity v, that distance is contracted by a factor of gamma. That's all that says. And the other equations, y prime equals y, z prime equals z, that's just saying that the transverse distances are unaffected by the boost. So then I can take the distance r prime, okay, that's x prime squared plus y prime squared plus z prime squared, and just evaluate it now in terms of x, y, and z. Okay, I get a factor of gamma squared in there in front of x squared because there's contraction in the direction of the boost. So therefore now I can write for you the force in the frame S in the x direction, y direction, and z direction. I just plug those facts into the transformation for the forces. Well, looking at this formula for a moment, I see that each component is scaled by a factor of gamma. And so I see the ratio of f of x to f of y to f of z is in proportion to x to y to z. Okay? So I learn that the force is radial. Okay, the particle is moving by, okay, at a velocity v, but the force that the particle at rest in the lab frame feels is still radial. It's not spherically symmetric, okay, like we would have in the frame S prime. In the frame S prime, okay, we have a particle, a charge Q1 sitting at the origin. It makes a radial symmetric field around it, like that. Well, we don't have that in the frame S, but we do have a radial force as well. F points in the direction R. That's what we learn. So it's a radial force, but of course it's not symmetric. We want to make a picture of it in that particular case. Okay. So we see that the force F is equal to gamma K Q1 Q2, and then it points in the direction R, and it's diminished by the factor R prime squared, and R prime squared is just what's written here. Okay. And so it's diminished by a factor of gamma squared R squared plus Y squared plus Z squared to the 3 halves, because I have distance to the cube over distance in the numerator. The force falls like 1 over R squared, and I've just written it as R divided by R cubed to capture that. So we can write the force, and then we can write it in terms of an electric field. We pull out the charge of the sink. Okay, the particles being moved about, and so the electric field E is characterized just by the charge of the source, and we can write a formula for it. Okay, and here it is. Okay, and I notice its characteristics. It looks like a pancake. For example, if I look in the transverse direction, okay, so that x is equal to 0, I see that it's enhanced by a factor of gamma. So the faster the moving particle goes, the stronger the field is transverse. Okay, and I can look in the forward direction for x different from 0. Okay, and then I see that as gamma grows large, this term gamma squared x squared wins. Okay, and so the force in that direction falls like 1 over gamma squared. So the force in the x direction is diminished by the motion of the particle. And the electric field is radial. I promised that. Okay, but it's not spherically symmetric. It's a pancake shape. E is radial, not spherical, and it's a pancake. Like that. Okay, and so we see that the Lorentz contraction plays an important role in the shape of the electric field. That's in distinction to Newton's case, where the velocity of the particle does not affect the electric field at all. Why is that the case? Well, the velocity of the source doesn't affect the forces. Right? Remember, forces and acceleration are Galilean invariant in Newton's world. Okay? If acceleration is unaffected by the boost, then it must be that the electric field is unaffected by the boost, and the electric field therefore is spherically symmetric in the moving frame and in the lab frame as well. And we can check that. Okay, we can check that in the Einstein formula here, in the formula for special relativity, because they take the case that the velocity is small. The velocity between the frames is small compared to the speed of light. Okay, that's the case where we should get back to Newton's equations. We have a velocity very small compared to the speed of light, and Newtonian mechanics should be good approximation to Einstein mechanics. So that means gamma goes to 1. Okay, in that case, F is just R over R squared. R squared to the 3/2. The gammas go to 1, and so I see that the electric field is spherically symmetric, and the force is unaffected by the boost. Okay, and so the formula makes sense. Okay, in the sense that when the velocity between the frames v goes small compared to c, I reduce back down to what I expect from Newton's theory, and that's fine. And then if gamma is very large, I get this strong pancake, this flattening of the electric field. That's due to Lorentz contraction, and that makes sense as well. But I have to think from Einstein's perspective then. Okay, so that's fine. So now I know how electric fields transform for point particles, and now I'm interested in the case where I observe the field generated by the moving particle from the perspective of a moving particle in the frame S. So now the force between two moving charges. This exercise will uncover magnetic forces, and I'll take one geometric configuration and work it through. Okay, and then in the textbook there are other geometric configurations which work through and give the same sort of result, the same general result that we have here, and we're just working through a special case. So I'll let Q2 have a velocity u in the frame S in the y direction. Okay, so it's moving in the y direction at time t equals 0 with a velocity u, and I'll say that u lies in the xy plane. I just jigger my y plane so that that's true. Okay, I just rotate the y and the z axes around the x-axis until that's true. I just define the y-axis that way. It's not a special situation, it's just a good labeling. Okay, Q1 remains at rest in the frame S prime, so I know what F prime is again. I'm not changing that whatsoever, so I know what F primes of x, y, and z is, and they're written down here. Okay. So now the next thing I need, I know what I'm given y u in the y direction in the frame S. I'll need to know what the velocity of Q2 is in the frame S prime. Okay, but that's easy to do once I know what u is in the frame S. I can get it in the frame S prime just by boosting, just by the addition of velocities, and that's particularly easy. In this particular case, u in the x direction and u in the y direction is 0. So I look back at how to transform velocities from one frame to the other, and I learn that the velocity in the S prime frame in the x direction is minus u. Well, of course that's obvious, right? That's why the particle is not in the S frame. The particle is not moving in the x direction. So if the frame S prime is moving in the positive x direction by a velocity v, it sees a particle which is at rest in the frame S as having a velocity minus v in the x direction. You can plug that into the law of additional velocities, or you can just write it down like that. And then you can infer also from those equations that the velocity in the y direction in the frame S prime is related to the velocity in the y direction in the S frame by a factor of gamma, and the gamma is just coming from time dilation. Plug into the formulas or just think it. And then the velocity in the z direction is 0, simply because I've arranged things so that all of the motion is in the xy plane. There's nothing going on in the z direction. Okay, so now I know the velocities in the S prime frame. I know the forces in the S prime frame. I can transform the forces into the frame S because I know the transformation law for forces. Okay, so I transform to the frame S. So just do that. Just take our formulas for the transformation of forces from S prime to S, plug in these values for the velocity in the frame S prime, and you'll get this interesting equation. You'll find that the force in the x direction consists of two pieces. There's one piece which goes like k q1 q2 gamma over r prime squared, okay, times x. The x over r prime again is just the unit vector in that direction. But then there's an extra term coming from the f prime dot u prime term in the frame S prime. And I've written that down, here, and it behaves like v from the Lorentz transformation, and then u sub y from the f dot u prime term, and it's u in the y direction times the f in the y direction, so it brings it back to y in here, and all divided by c squared. So take a moment and plug these two conditions into your equation for the transformation of forces between the frame S prime and S, and check that this is correct. Okay? Okay? And I promised you before, of course, that forces in special relativity are going to be velocity dependent, and here we see it very clearly in this particular example. The force in the x direction is proportional to v, the velocity between the frames, times the velocity of q2 in the frame S. That's u sub y. And then there's the force in the y direction and the force in the z direction, and similarly check on those. Well, clearly I'm particularly interested in this extra term, which has no Newtonian analog. So I call that f sub x, and I write comma mag, M-A-G, for magnetic, because we're going to identify this with magnetic forces when we use conventional notation. Okay, but we've discovered it. We haven't done anything conventional here. We've just transformed from one frame to the other in special relativity, and we've discovered a new term, and we're going to call it magnetic, and that'll make sense as we proceed. So here it is. I've just written it out, the second term. It's an example of the Lorentz Force Law. Now, the conventional way of writing the Lorentz Force Law, we want to couple into it, because the Lorentz Force Law will encompass all of the possible geometric situations that we can imagine for the charge Q2 moving in frame S, and the force can be written as the vector force is equal to Q2 times sum of two terms, the electric field plus U cross B. Okay, the velocity of the particle in the frame S crossed into a new field that we're going to calculate, called the magnetic field. We want to check that phenomenological form fits the equations that we'll be generating here by fundamentals, and we want to identify the magnetic force. Okay, and all of these expressions are evaluated at the position of the particle at the moment t and r. Okay, so here I can take this force, right, and I'm interested in taking the case, looking at the component in the x direction, okay, and then identifying my Q2 U cross B in this particular case. Okay, so go back here, and what do I see? Okay, I pull out the factor of U, U sub y, and everything else left behind. Okay, I pull out the factor of Q2 and the factor of U, and everything left behind is what I call B. That's what the formula says. So that's all I've done here. I pulled out Q2, and I pulled out U sub y, and then I have B, the magnetic force left behind. I see that it's proportional to the velocity V. That's the velocity of the charge Q1 in the lab frame. Okay, and then it has these other factors in it. The point is, it's proportional to Q1 times V. Q1 times V. That's the current generated by the moving charge Q1. That's the important point. Okay, but anyway, I'm just matching this formula to that formula at this point, and I have a little more work to do concerning cross products and directions of forces and B fields. Okay, but anyway, now I've written F sub x is equal to Q2 times the electric field in the x direction in frame S plus U sub y times B, and I've identified here, okay, that what B is. Okay. Now I want to think, however, about the directions of the various forces, fields, and vectors in the problem. Okay, so the force, that's in the x direction, okay, and so I want to take a look at the magnetic field. The vector u, the velocity of the particle here, points in the y direction. I have to cross it with a magnetic field and get a force in the x direction. So therefore B must point in the z direction by the right-hand rule, so that U cross B points in the x direction. So I see that B, therefore, which in magnitude is given by this formula, can be written as this prefactor and then V cross R over C squared. Okay, because V cross R just reproduces V times Y for the component B in the Z direction. So just check my vector products there. Okay, just check that V cross R works out so that B points in the x direction, and that's easy. V, for example, points in the x direction, and so that cross product points in the in the appropriate direction. Okay, so that in the direction so that U cross B points in the x direction. Okay. Okay. So taking this formula, I see I can take a B. B is just this formula, and I can pull out the scalar pieces of it. Okay, there's a V cross R over here to get me a vector which points in the z direction, for in the case that V points in the x direction. Okay, and that R lies in the xy plane. Okay, in that case, just write out the cross product of V cross R in the case that V points in the x direction, and then you see that and then you see that B points in the appropriate direction, so that U cross B points in the x direction. Okay, a little bit of geometry to do, a little bit of cross products to do. It's pretty easy stuff. Okay, so there you are, and then I can write it in this way as 1 over c squared V cross okay, a formula with gamma k q1 over r prime squared times v, and then I can recognize from my previous exercise in how electric fields transform from one frame to the other, to identify this stuff in the parenthesis as the electric field in the frame S. Okay, from the previous example. And so I see the magnetic field in the frame S is equal to 1 upon c squared times v cross E, where v is the velocity of the source. Okay, so that's an interesting result, which has lots of implications. Okay, and then in that situation we have the Lorentz Force Law, and we see that there's a magnetic force which is generated by the boost, and everything holds together. Okay, if we take other geometries for the vector u, I've just taken u to be in the y direction, but I can take it as a linear superposition of velocities in the x direction, the y direction, and do more work. I can get further examples that the force law of Lorentz covers all these cases. And so check that out in the text. Okay? So in the text you'll see arguments that the Lorentz force law is as written down there, that the force is equal to Q2 times, in parenthesis, E plus U cross B, and you'll get the formula for B in the case that it's generated by a charge that moves in the x direction with a charge magnitude of Q2. Okay, and then you'll get the force in any particular situation that way. So do more general cases than that. Okay. Now, one of the things we learned from this example is that magnetic forces do not satisfy action-reaction. Okay, and here I've written down a simple example. Here I've just imagined that I have a force, that I have a charge Q moving to the left with a velocity u, and I have a charge Q with a velocity moving perpendicular, like that. Okay, and now I follow the Lorentz force law, and the fact that the magnetic field is given by velocity of the source vector cross into the electric field, to calculate what the forces are, the magnetic forces are, from this current influencing this current, or this current making a magnetic field and influencing that current. So let's go through that. Okay, so this charge Q is moving in the velocity in the direction u. Okay, so it generates by the right-hand rule Q cross B a B vector, a B which points out of the paper. Okay, if it points out of the paper, then you see that B cross V points in the direction of minus x. Okay, so that's the magnetic force that this charge with velocity u makes on this charge with velocity v. And then similarly, the charge that has velocity v makes a magnetic field. Okay, it's given by the right-hand rule, okay, of v cross E around it. Okay, so it points out of the board like this. If it points out of the board, okay, then I see that u cross B points in the up direction by the right-hand rule. B is out of the paper. U cross B is up, so it points in that direction. Okay. Oh my God. So the forces of one on the other, well, they point in the wrong direction. One points up, the other one points in the lateral direction. They can't sum to zero, right? So magnetic forces don't satisfy Newton's third law. Okay, and that's significant. Okay, of course, because remember, Newton's third law is so essential in Newton's world to generate momentum conservation. So momentum conservation in Einstein's world is going to involve new ideas. And I've already indicated what those ideas are. That the electromagnetic field is not just a constraint equation, it's a new field. It carries energy, momentum, and angular momentum. And it's going to come and save the day. Okay, it's going to save the day, so the total momentum of the system is going to be conserved in time, even though we have this unexpected result. Okay, but that's the kind of thing we'll be doing later on, because we have to develop the idea of the electromagnetic force in more detail before we get there. Okay, so that's all that I want to do at this point. So at this point, we've derived the Lorentz Force Law. Well, I've done one special case of it. And go to the textbook and go to the problems, go to the recitation section where we'll work through a whole bunch of problems, which will convince you that the Lorentz Force Law is a general result and that we can obtain it by arguments like this. Okay? Remember, in these particular cases, the velocity of the charge Q2 was essentially arbitrary. Okay? We took a snapshot at a particular moment to do the argument, but the velocity is changing and is affected by the forces involved, and so actually it's rather general. We're doing transformations between instantaneous rest frames or instantaneous frames, and we can cover all cases that way. Okay, so in the next section of this lecture, we'll discuss the transformation of the electric and magnetic frame fields between frames.